In this video, I'm going to be conducting an one-way Anova in Excel. I won't talk too much about the background of Anova, the theory, but I'll focus on primarily how to do it in Excel. So the situation is that we have 4 synthesis methods here that we would like to test. They produce a yield in percent of the theoretical maximum that you can see here, and we tested each method 5 times, 1, 2, 3, 4, 5. And what we would like to know is there any significant difference between the yield that these methods produce? So in terms of a hypothesis, what we would like to answer, or the hypothesis that we would like to test, is, let's call it the null hypothesis, is the means of these 4 populations. Is it the same? Are they the same? So that's the hypothesis. Now the assumption is, and I'll put that here, the assumption is that all these 4 samples come from 4 populations that have the same variance. So the variance from population 1 is the same as the variance of population 2, is the same as the variance of population 3, and that of population 4. Now that's an assumption. If that assumption is not fulfilled, it may not be critical, because the Anova is quite robust with respect to this assumption. But nevertheless, that's our working assumption here. And what we're testing is the hypothesis that not only do these 4 populations have the same variance, they also have the same mean. If that's the case, we might as well consider these to come from the same population. The alternative hypothesis is that the null hypothesis is false. So we're not digging into whether mu1 is greater than mu2 or different from mu2, or mu3 is different from the others, or anything. The Anova cannot answer that question. The only thing the Anova can tell us is, are they the same or are they not the same? So of course, if we can reject the null hypothesis, well, then the null hypothesis is false. And now let's do the Anova. And I have to apologize for this being in Danish, but I'll do my best to translate along the way. So what you do is you go into data here in your menu, in the top menu, and then you choose data analysis. If you don't have any menu item called data analysis, that's because you need to install over here. You need to install, you go down to settings, I believe it's called in English, and you choose plugin, add-in, maybe it's called, and then you choose the analysis tool pack here. That's the one you need to install. And then you go into data analysis, and here you get some different statistical tools, and we need the Anova one-way Anova. Single factor, I believe it's called in English. So I'll choose that one. And then we need to decide whether our samples are grouped by rows or columns. In our case, I think the default is columns, but in our case it is actually rows, because this is one sample, this is another sample, and so on. And we can decide whether we have these labels in the first column. In my case, I do have labels. These are the labels that name each sample. So I want to include those in the input area that I have to specify right now. So I'll click this one, and I can specify the input area here. including the labels over here. Now the level of significance is 5% here by default, and I'll just keep that. And if you want the output from the Anova in a different sheet down here, you can choose this option here. But I want the output in the same sheet here, so I'll just keep it like that, and I can choose where I want it, and I think my upper left corner will be here. So all we need to do now is click OK here, and then we get the Anova output, which is in Danish, sorry. Up here we have some intermediate results. We computed the sample size of each sample, which is 5 for each of them, the sum of the observations here, and here we have the average of each sample, and here the variance for each sample. So down here we have kind of more concluding figures. This thing here is, I'll just replace it, between groups it says, and here that's within groups. So what that means is that we're computing the sum of squared deviations. I believe it's called SS in English. The sum of squared deviations for each. Well, in this case it's within the group, so that means that we're computing the sums of squared deviations for the first sample, and for the second sample, the third and the fourth, and then we find the sum of those. And that gives us 28. If you don't know what the sum of squared deviations is, it's kind of the same as the variance, just not divided by the sample size. For between groups, the sum of squared deviations is the averages here, and then we compute the variance, or the sum of squared deviations for this sample here, the sample of averages. Okay, so that's why this number here has 3 degrees of freedom. It's computed from 4 data points, the averages of each sample. But in order to compute the sum squared deviation, then we need to compute the average of these 4 data first, and then we can compute the sum squared deviations. That means we used up 1 degree of freedom, so all that's left is 3 instead of 4. For this number down here, how did we compute that? Well, we computed the sum squared deviation for the first sample. In order to do that, we need to compute the average of this sample, so that uses up 1 degree of freedom. For this one, also we have to compute the average and use 1 degree of freedom to compute the sum squared deviations. Same thing for the third and fourth sample here. That means altogether, in order to find sort of the average variation or sum squared deviation, we take this number and divide by 16, not 20, even though there are 20 observations, but only 16 because we used up 4 degrees of freedom along the way. And when we divide by 3 or 16, we get these numbers here. So this is 72 divided by 3. These numbers are what we could call the mean squared deviations, or the mean variation between the groups, between the methods, and within the methods, the groups here. So you can see that there is much more variation between the groups than there is within the groups. And that's important, because that tells us that, I mean, why are these numbers different? That's kind of the basic question. Why don't we get the same yield every time? Well, part of the answer is that each method produces different results every time you use it. But there's another answer to that question, and that's the choice of method makes a difference in the yield. And right now it looks like the choice of method is much more important when you need to explain the difference in yields than the you could say, random variation that takes place within each method. That's really the two things that we are comparing here. And how do you compare two different variations or variances, if you like? Well, you use an F-test. You take the ratio of those two numbers, the two variation numbers, and you get an F statistic. And you know the distribution. It's an F distribution with 3 and 16 degrees of freedom. So you can compare this value to a known distribution, and also you can compute a p-value. In this case, the p-value turns out to be very small. It's just about 0.01%. So it's a very small p-value. And that means that we can reject the null hypothesis at significance level 5%. That is to say, these four methods produce significantly different yields. The Anova does not conclude anything about which method produces a different yield, or whether two of them produce different yield from the other two, or anything like that. It just says that there is a significant difference between the four methods. The critical F value out here is the threshold value beyond which we would reject the null hypothesis. And as you can see, our test statistic is way above the critical F value. It would have to be less than the critical F value here if we were to not reject the null hypothesis.